With that said, I want to introduce you to one more mechanism that you have in Async I/O, that is the exception group. Let's take a look. Here's the setup. If we had multiple asynchronous tasks, and one of them errored out, and we're running them concurrently, what should we do? So our typical model, and our simplest way of running these things concurrently, is to just use gather. So here we might do something like gather, task AAA, and task BBB. And of course, we have to await this like that. Now, if one of these errors out, what should our program actually do? Well, gather, by default, just cancels anything that's remaining. Gather just stops at the very first one that errors out. If it were the case that, for example, we wanted to keep going, how would we manage that? Like, what if we wanted to run task AAA and task BBB, and if one of them errors, we don't necessarily want everything to error out? Well, if we look at the help text for gather, we can see that it provides us with a way to do this. There's an extra keyword argument, returns exceptions, that by default is false, but if we say returns exceptions, what we'll get is we'll get the, and let's see, returns exception. Let's get that one more time. Return exceptions, that's what it is. You can see we get the actual exceptions. It runs all of them and it returns the exceptions. Well, let's change this very slightly. Let's make only AAA error out. And here you can see, oh, yeah, but we didn't get the result values. Well, that's kind of a pain. Kind of want to have both the result values and we want to have the exceptions, and we want to be able to distinguish them from each other. Of course, we don't know if this thing might actually return a value, so there might be some ambiguity whether it's actually returning a value or not. And so we have these different modalities of what happens when an error occurs. Exception groups are an extension to the Python syntax to allow us to handle multiple exceptions that might occur as a consequence of multiple things running concurrently. If we think about how exceptions typically work, with exceptions we typically have one line of code, and that line of code has some flaw in it, like it's calling a function that divides by 0, and we decide to do something about that exception, that 0 division error. But in the asynchronous world, it's very likely that we might have one line of code that goes off and does multiple completely separate independent things. And what are we supposed to do here? We're supposed to catch an exception. Which exception are we going to catch? What about the remaining tasks? Are we going to terminate everything? Gather allows us to continue to run everything. But, and let me show you one small detail of this. Let's move this print to the bottom. You can see BBB still ran, even though AA errored out. But we've lost some kind of fidelity over our error handling. What exception groups give us the ability to do is to group exceptions together. And the mechanism is actually quite straightforward. So let me show you the basic mechanism. We can create a group of exceptions. We can give it a name. And this is just some grouping of multiple exceptions that might be raised as a consequence of going off and doing multiple actions asynchronously. So here, let's say a 0 division error and maybe an index error. This can be raised, and we get a slightly different output. If you remember, in our universe of exceptions, it's the case that we have not only just regular individual exceptions, but we also have some chained exceptions. That is to say, we can also say, oh, re-raise this exception, maybe as a value error, from this exception here, and you can see that we get this chained exception where we have one portion of the exception here changed to this. So you can see we have some kind of serial chaining of these. Well, the exception group is just some kind of parallel chaining. It's grouping together some exceptions and saying here are all the exceptions that were raised. Now let's do the following. And it's just an exception like any other. So you can see we can, if it's raised, we can catch it. But what the exception group gives us the ability to do is it gives us the ability to handle multiple possible exceptions within multiple different branches. Typically, when we have one line of code, we have some exceptions that we order from most specific to least specific. So, for example, the zero division error is more specific than, say, accept exception, or if we had something like a lookup failure, we can try this, and then we can say this is a index error at its most specific. And slightly less specific than that would be a lookup error. And of course, less specific than that would be some accept exception, and then the least specific would be a bare except, which we really shouldn't do. And so we have these ordered in some fashion, and we trigger the first one of these that most specifically matches this. So here, this would be an index error, but if this were, say, a dictionary lookup, that would be a key error, so it would skip over this and hit the lookup error, and we never hit the exception. Or if this were a zero division, it would pass by both of these and hit the exception. Well, with some special syntax, we can indicate that a try except can catch multiple possible exceptions and handle each one of them. If we put a star after the except, what we're indicating is that this try except block can handle this exception as well as this exception, and they are no longer exclusive to each other. So if we look at this and this, we can see we actually handled two branches of this, whereas typically without that star, we can only handle one branch. Here we have some ability to do this. Now, how do we actually use this? Well, consider the following. Let's say that we have some mechanism that's going to run queries, and we worry that those queries might fail. Maybe they're creating tables, and maybe the tables already exist, whatever the case may be. So we have some sequence of queries that we want to run, some of which are good and some of which are dodgy. So here, let's do this. Let's say this here is missing something, and let's say select star from does not exist. So here, this is fine. This is a syntax error, and this one's going to be some other database error. Let's dedent this. Like that. And let's put this into our asynchronous entry point. Like that. Let's launch into our entry point. And let's say for each one of these queries, we're going to run them against our database. Now, obviously, for each one of these, we could put a try except around this and catch this individually. So we should see two of the ones that don't exist, the syntax error and the no such table. We could gather these together. Like that. And then, at the very end of this, we could do something like the following. And we could then, on the outside of this, say, okay, what we're doing is we're giving ourselves the ability to run multiple queries, and for all the queries to be run, but if some queries fail, for us to have the ability to deal with those queries. Now, in truth, this is maybe a little bit hokey because, for example, we don't know which query exactly failed, although we could pull that from the exception data. But here, let's go for operational error. So let's pull that from SQLite3. Import operational error. And let's just print it out here. And we have our full fidelity of, and let's raise that exception group. That's good. That's good. And here, this should be a, that's good, that's good. This is both of them. We want just the one of them. So here we raise that coming out of this thing. Just quickly take a look. Yeah. So there we go. And we have the exception group with all of the operational errors. So I guess we need to do, we'd have to distinguish these. We couldn't distinguish both. So this is the group with both of the operational errors. Otherwise, if we had, let's say, a little bit tricky to find something that won't be an operational error here, maybe if we try and pass some data in here, we might get a different type of error message. And that's good, and let's do a select one with, yeah, there we go, programming error. So if we get a programming error as well, we can see, you can see we get two of these blocks hit, one of them with all the operational errors and one of them with all the programming errors. And we can create an API that allows us to run all of the code and get all of the errors, because it may be the case that, you know what, we expect some of these to fail, we expect some of these to succeed. Maybe there's some fallback mechanism. Maybe it tries one thing, and if that fails, it tries the next thing. But we still want to get those errors out. Well, the exception group gives us the ability to raise multiple possible exceptions from one unit. It does multiple pieces of work, and to have them all handled nicely. And in the absence of that, if we didn't have this special syntax, all we'd be able to do is accept on the exception group, and then we'd have to unpack this thing and figure out what's contained within it. Well, you can think this except star syntax gives us the ability to group these together and to work with exactly the ones here. So you can see we've got two operational errors and one programming error. It gives us the ability to subset these to the types of errors we have. And then, of course, we could do something about these as we see fit. And so in conclusion, when we are writing APIs, basically functions or libraries, functions, modules, libraries, or classes that are async aware, we need to think about error handling. If multiple asynchronous tasks could run and could error out, then we need to consider what to do when one errors out. If the remaining should continue to run, and we need to report any errors back, then we can use an exception group. Similarly, when we are using an API, well, we should be aware that that API may raise an exception group, one per asynchronous task, one exception per asynchronous task, as opposed to one giant exception representing all of them. So we need to be aware of this both on the raising side and also on the accepting side and the catching side, that our APIs may do this. When we work with gather predates a lot of this mechanism, so it only has that return exceptions keyword argument. But any new API that makes use of things like task groups and exception groups, you may see any new API that exists maybe only in the last couple of versions of Python, you need to be aware that you might get exception groups back, and you need to be aware of how you might want to handle them using this except star syntax. Finally, the last thing that I want to briefly talk about, and very, very briefly talk about, is context variables. I said I wouldn't talk much about threading, but one of the things that comes up quite a bit when we deal with threading is we need to have some sort of state that is local to each individual thread. And what we come up with is thread local state. When it comes to asynchronous code, well, we can't use thread local state because everything is single-threaded. And if it's the case that we need to pass data between asynchronous units, and those asynchronous units do not form a very clean hierarchy of, say, F calling G, calling H, well, we need to have some way to pass data in between them. If they form a strict hierarchy like this, well, the way we pass data is we just pass data down. Here we have some data, and we pass it down to here, and then we pass it down to here, and we pass it down to here, and we pass it down to there. And if it's the case that this splays out, maybe this is gathering 2 of these, well, this can still be mutable data, and it'll still be mostly pretty easy for us to understand what's going on. Here, we can think that we have 3 units, and they can all be appending. We don't know exactly which order they'll append in, but we won't run into any data corruption as a consequence of this. But if it's the case that they need to share data and they're not strictly connected in a hierarchy like that, well, what do we do? In normal synchronous code, well, we create global variables. So if we can't communicate between F, G, and H, because they're not in a strict hierarchy, but they may all need to work on the same data, and only one piece of data, well, we typically create a global variable. But if we're in a multi-threaded scenario, we can't do that because they'll all have access to that one same global variable across all of the threads, and if one of them changes it in one thread, everything blows up, so we have a thread local variable. Context vars are basically the idea of thread locals, but adapted to support async IO as well. And it's just the ability for us to create some data that can be viewed among multiple different asynchronous tasks, such that each one of those asynchronous tasks can communicate via that piece of data without accidentally clobbering it or without accidentally stumbling upon each other. So I'll show you a very, very quick example of this. This was added in Python, in very recent versions of Python, about 4 or 5 versions back. We have a context var, takes a name, and we can set a value for this. So here, let's set an initial value. Here we can get a value out of this thing, and then we can set a value. And then we can set this back to the original value. We can do this in an asynchronous task that calls an asynchronous task, like that. And we can see that if we do this, here's a before and an after. And if we, in our entry point, launch 2 of these, here we'll do this with async with task group stg. We'll create 2 of these that run together. There we go. We'll see that we have the ability to transmit data down each one of those without explicitly passing data from F to G or from the main to the F to G. And you can see that they're independent of each other. So if we say this is branch 1, this is branch AAA, and this is branch BBB, we'll explicitly pass some data down, like that here. You'll see, and here let's make sure that we need to put an await here, just so that this doesn't get serialized. There we go. You can see the interleaving, but you can see that they're actually independent of each other. So we have something that can appear to be a global variable, but is actually something more akin to a thread local variable, except it's not limited to just storing data per thread. It can store data per each one of the asynchronous entities within our event loop. And you can think of this as kind of a generalization. The general idea is we need to pass some sort of contextual information between units of computation such that different parallel units of computation don't interfere with each other. Different hierarchies or different call graphs or different subtrees of these call graphs don't interfere with each other, such that it's async aware, and such that we don't have to explicitly pass this from function to function to function. We can pass this through something that looks like a global variable. Now, that's a very abbreviated introduction to context variables, but in general, you can think that there exist async IO methods or mechanisms to mimic traditional mechanisms like context or thread local variables. And of course, we'll leave that for your future discussion. With that said, thank you all for joining us for this session. I know this was quite a bit of a rush trying to squeeze in all the mechanics of async IO. If you do have questions, feel free to share it with us in Discord. We have many other sessions on async IO. We'd be more than happy to share those with you as well. With all of that said, thank you all for joining us, and we'll see you all next time.